thermal and fluid sciences, interfacial phenomena, scalable nano manufacturing, and renewable energy. He is an ASME fellow and a recipient of several prestigious awards. To list a few, he is an NSF Career Awardee. He has the ACSPRF Award, an ONR Young Investigator Award, as well as the Young Investigator Award in Heat Transfer from ASME. With that, I'm really happy to invite you, Nenad, for our seminar today, and the floor is yours.
Okay. Thank you, Rohini. Let me see if this helps. Hello? Okay. Maybe I'll wear this just so I can project better. Perfect.
Yeah.
So thank you, Rohini, for having me. Thank you, everybody, for being here. It's a pleasure to be at Michigan. It's a great sister school to Illinois, and I know a lot of the faculty here. I see Solomon here. I saw Andre earlier. That we actually go way back. We were colleagues in graduate school, and actually for Solomon, I like to say that I convinced him to come to MIT. Maybe it didn't take too much convincing, but I'm glad he did, and I'm glad he's doing great work and with Rohini's lab as well. Today, I'll talk to you a little bit about some of the work we do on tailoring surface chemistry and surface roughness for enhanced two-phase processes. But before I start, I thought I'd tell you a little bit about myself and why is it that the things that we do, why do we do them? The main motivation for our work is we like to understand nature design. So why many plant and insect species tend to evolve surface roughness or surface chemistries for certain functions. So to give you an idea, this is previous work we've done on Neotibicin cicada species, which if you were to put them in an AFM or an SCM, you would see these highly ordered pillars that actually have multiple functions. They give optical transparency, they're antibacterial, they're super hydrophobic, they remove water when it beads up on the wing. And what we like to do is actually use these types of surfaces, learn from them, and then mimic them for energy and water applications. Specifically these days, looking at decarbonization and electrification. In many applications, things like power gen, which I'll talk about today, distillation, desalination, HVAC and R, heating, ventilation, and air conditioning systems, thermal management of electronics, which I'll discuss a little bit, and then even manufacturing. And these are kind of some previous examples of work looking at high temperature liquid metal wetting, frosting on heat exchangers, collaborations with the Abbott power plant in Illinois, which I'll discuss today, and then cooling of gallium nitride semiconductor electronics. So, you know, a picture's worth 1,000 words, a video is worth 1 billion. This just gives you a snippet of the different kinds of things that we work on. We're heavily an experimental lab, and we study phenomena from the fundamental scale, ranging up to very applied technologies. So things like icing physics and bridging and nucleation on super hydrophobic surfaces, scale up to large scale heat exchangers. This is a super hydrophobic heat exchanger. Interestingly, this is a heat exchanger made by a company called Brazeway, which is in Troy, Michigan. This is a Michigan product that's actually sold in the US and across the world. Looking at liquid metal flows on rough surfaces and how we could actually save silver-based braze materials using surface roughness and chemistry. This is a jumping droplet surface cooling a gallium nitride semiconductor device. This is about 5 or 6 millimeters in dimension, ball grid array device with PCB on top. And so using condensation to kind of help cool. And then things like non-aqueous working fluids, hexane, ethanol, refrigerant condensation on functional surfaces and trying to achieve dropwise condensation. So I could kind of describe the lab as using 5 different axes that we work on. We span length scale from micro nano length scale, looking at two-phase flow physics, all the way up to scale up of real large scale heat exchangers on the order of 10 meters. We span temperature scales. We look at cryogenic things like flow boiling of liquid hydrogen for aviation fuel cell applications. All the way up to 1,000-degree times temperature scales for high temperature materials and heat exchangers. We span surface tension scales, things like refrigerants, you know, down to 5 millinewtons per meter, all the way up to liquid metals, and then time scales, right? Droplet coalescence, hydrodynamics. You're talking about microsecond time scales, all the way up to long multi-year durability studies, you know, 10 to the 7, 10 to the 8 second time scales. And the one that I really want to, the 5th one is this scale at the bottom, which. And I'm glad there's lots of students here because usually when you come to a place like like Michigan, people tell you this is what you want. You really want to stick with fundamental, this, don't worry about it. But in reality, if I had to give you a piece of advice, it's great to span this scale as well. If you could do both of these, both in industry and as a faculty member, hopefully someday you will become faculty, you could do so much more. You could have much bigger impact. And my talk today, I'm going to try to kind of bridge these two by giving you a few examples of where we started here, 8 years ago, and we're currently here now, and kind of to show you some impact, some real impact. Okay. Most of the work that we do, as you could already tell, is with surface roughness and chemistry, so coatings. And I like to show this kind of Venn diagram of something that I call the coating conundrum. For thermal applications, the kinds of coatings we want to put down on heat exchangers and real systems, you want them to be thin because you want to minimize the parasitic thermal resistance. You don't want it to affect your overall heat transfer coefficient. But if you want things to be durable, you want them to be thick. Right, think of like your Teflon coated pan, where you're putting down maybe 100 microns so it lasts, right? You don't want it to fail. Combining these two is pretty simple with hydrophobicity. Now, when you add in things like low surface tension liquids, where conventional hydrophobic surface chemistries don't work, this becomes very difficult. And ideally, where our lab likes to play is here. This is kind of like where I say where we want to be, okay? Now, why is this so hard? I mentioned hydrophobicity and surface function. It's actually a wicked problem. This is a term we use in the Northeast. Many of you have heard this before, but a wicked problem is a very complicated problem where there's not a linear, straightforward solution. And the reason is because you really want function, you want thermal properties, you want mechanical properties that are sometimes very counterintuitive. So for example, if you look at a material surface energy for things like clean metals, oxides, polymers, and noble metals, typically, the materials that have higher durability, like metals and metal oxides, they have high surface energy, which is what you don't want. You want low surface energy. Then if you look at things like thermal conductivity or thermal properties, metals have high thermal conductivity, which is what you want from many thermal applications, but they also have high surface energy. And so in reality, the materials you're left with here are polymers. And polymers have very poor mechanical properties. You can see here in the ultimate tensile strength as a function of Young's modulus. Polymers are down here, but ceramics and metals have great properties, but they have very poor functional properties. So because of this, for thermal-based applications, you want low surface energy materials, but they have poor thermal conductivity, typically less than 1. Good thermal conductors like metals have high surface energy, which is not what you want. And low surface energy materials have low Young's modulus. Again, we just talked about polymers. And so you're at this interface where you're really trying to develop materials which have good durability, can last, can give you the enhancement that you want over many years, ideally, but have the mechanical properties which really don't work for you, okay? So why is this important? And I think the way to motivate this well is through a direct application, which I hear some of you are learning in your heat transfer class, which Andre just walked in. He mentioned that in Dropwise condensation. This is a process which is used by many power plants. So typically in a Rankine cycle, you have your condenser. The condenser actually converts your post-turbine steam into liquid, which then gets pumped back into the boiler and you produce steam. And this process is used absolutely everywhere. Naval systems, stationary power plants, all over the world. Typically, these are film-wise condensing, meaning that it's just a clean, bare metal, and you form a thin liquid film, which the liquid accumulates and falls off the surface, and it gets recycled. In the 1930s, a gentleman by the name of Schmidt identified that if you put a animal fat on the surface, you could undergo a thing called dropwise condensation. And essentially, all that happens is you start forming discrete droplets, which once they get large enough, they'll coalesce and they'll shed because of gravity. And when they shed, you'll see this cleaning process. When you clean, you then allow exposure of fresh vapor to condense on the surface. And this highly transient process ends up giving you 5 to 7x higher heat transfer rates when compared to film-wise condensers. And so why is this important? I already mentioned, if you just look at steam-based power plants, so things like burning natural gas, nuclear, coal, that's about 85% of the world's capacity. And that also uses 100 trillion gallons of water each year, fresh water, to actually cool these systems. And so the adage I like to say is, even if you could instill this process, you're talking about an overall 2% efficiency increase in the overall plant. So forget about the 5 to 7x higher heat transfer coefficient in the condenser, for the overall plant, you're talking about 2%, but 2% of 85% is a lot. And that 2% actually equates to all of the PV installed in the world, the PV capacity. So you can actually save that just by using a process like this, okay? And so you might ask, why aren't we doing this already? This is a great idea, fantastic, right? Why isn't it utilized? Well, the main problem is durability. I mentioned polymers, polymeric materials. There's a lot of work. You know, this is a paper in 1986 by a gentleman at NRL, by Paul Marto, looking at how exposure to liquids over time and higher temperatures erodes these materials. And this has been a problem for the last 70 years, essentially. And so for 70 years, people have been working with this. There's been a lot of academic studies, but not a lot of progress on getting this actually installed and developed for a real power cycle. And so the way you see this is if you look at a heat transfer coefficient as a function of time, you'll start great, you know, yay, lab scale result, you go tell your advisor, but then within a half an hour, you're pretty much back to bare aluminum. And so it's no good, right? Great for Nature papers, but we'll leave this out. So we'll put this in the SI. Okay. So this is a big problem, right? And we have to overcome it. So when I first started at Illinois, this was like the obvious thing to work on. I graduated from a heat transfer lab, and every conference I went to, people would always put their hand up and say like, hey, what's the durability of this coating? And there's a lot of people that work on coatings, but they don't handle this problem. And so the obvious thing was to think, well, why do these fail? And can we understand why they fail? And can we develop better materials to make them not fail, right? To actually overcome this issue. And so we first started out looking at many different surface coating combinations. Typically what you'll see when you condense, this is an optical microscopy video. These are droplets, water droplets condensing from the atmosphere on a polymer coated silicon wafer. You'll see these blisters form, and this has been known for 30 or 40 years now. These blisters will form, they'll coalesce, grow, and then eventually you'll actually de-wet and the entire coating itself will fall off the surface. So what we noticed was, you know, whether we do PECVD, you know, like a PTFE Teflon-like coating on silicon, spin coating, things like polystyrene, Teflon, AF formulation, we see the presence of these blisters over time. And initially, you know, this was great. We could actually get repeatable results in terms of failure, but this really was limiting us because we weren't able to tell what's actually going on and what's causing these blisters to form. And so one of the initial things that we discovered just by careful observation was there's probably the presence of pinholes. Whenever we deposit these, even if it's CVD, there is going to be some pinholes in the surface just because of dust particles or the processing steps. The other way we actually observed this was when you look at when these blisters grow, so this is a time-lapse image, so from B to I, you see the blister grow right here, and these are droplets around it, and what you'll actually see is cross-communication between droplets. So this droplet here, number one, will enter the blister, but then it'll actually be injected into one of these two droplets here. So if it keeps growing, you'll notice the blue droplet will enter the blister and then enter this droplet here. And so there's definitely pinholes within this blister, which actually cause communication between your substrate and your liquid just growing on top. You might ask, well, what's the preferential mechanism of why one goes into the other? It's Laplace pressure, so you have higher curvature. This droplet has higher pressure than the droplet in here. So you actually have a driving potential to have liquid move from one to the other. And so this was a first indication of the fact that these blisters are very important. The way they start typically is with some sort of defect, and how can we now better understand how this delamination process occurs, and can we actually use something like mechanics to help us in that vein. So, you know, when we started this project, we worked with a gentleman named David Cahill. He's a material scientist. He's actually known to be a very sticky scientist, so he's all about rigor. We had to go back to the drawing board and actually identify, can we develop a system where we understand it really well to be able to then say something about how things like Young's modulus, thickness, chemistry affect blister formation and growth. And so this is the model system we work with. Very low roughness, silicon coated, C4 FX chemistries, right? So very smooth. We do Rutherford backscattering to measure things like density of our polymer films, FTIR to look at amorphous CF groups, XPS to look at the actual structure of the polymers we're depositing, and then TDTR to actually measure thickness, but also you could actually use time-domain thermal effectiveness to measure things like Young's modulus of your polymers. And so by combining all of these, we could then have a very well-characterized system to really understand how these blisters grow and what's actually affecting their formation. And so we use pretty simple top view optical microscopy. We limit the wavelength so we could actually do fringe counting. And so you could actually get things like central deflection of this blister as it grows. So delta would be at the center. What is the height as a function of the radius for different thicknesses of material? And then you could actually normalize this by the thickness of the material by this delta star. And this normalized radius, this actually comes from something called plate and membrane theory, which is a mechanics theory developed long ago, 60 or 70 years ago. And so you get nice behavior between the physics, and it tells you that plate and membrane theory is something which is very important for the deformation and formation of these blisters. By using things like diamond tip nanoindentation, we could then also study things like how does the shape of the pinhole and the size of the pinhole affect the blistering formation process. And so the model we have is that there's this pinhole that forms, water has access, it nucleates on the substrate itself because of the high surface energy. And then as the water propagates, it delaminates the coating and forces it to actually come off the substrate. And so you could actually see this in situ. This is environmental AFM, where this is our nano indentation. It's more micro indentation in this case. And by looking at phase imaging, you could actually see that water will form inside the blister and it'll fill it up. And then actually it'll cause this deformation to grow bigger and bigger. So if we look at an interesting result, what we notice is that if we have bigger size pinholes, so these are larger than the ones I'm showing you down here, you actually don't see blister formation. You'll have water not droplets nucleate, and they will actually grow up and above the coating. If they're small, what will happen is they'll actually form blisters. And you can actually clearly see this here. And this test was very interesting because we first thought, why does this happen? So it turns out by using that plate and membrane theory formulation that I showed before, you could actually develop this omega parameter, which is a non-dimensionalized pressure. Think of this as the Laplace pressure, which is being formed inside the blister, normalized by the elastic pressure of that membrane, which wants to stay on the surface. So you need some force to actually delaminate the coating. And so you could think of this omega as essentially, if this Laplace pressure is greater than the elastic pressure, then what will happen is blister formation will happen. So if you actually have this greater than 1, you'll end up seeing blistering form. If it's less than 1, you won't see. And that actually agrees well with our previous results because the Laplace pressure is normalized or proportional to 1 over the radius of the defect itself. And so essentially by using this formulation, we can now plot things like Young's modulus as a function of your wet adhesion. The wet adhesion is basically the adhesion of your polymer to your substrate, and what coatings we need to be in the durable regime for different Young's modulus and wet adhesion. So for things like high Young's modulus and high wet adhesion, the coatings thickness required can be pretty small, and you're talking about things like inorganic coatings. Where we are currently is down here, state-of-the-art polymers, where Young's modulus is low, wet adhesion is fairly low. So the coatings we need are 1 to 10 microns to actually stay durable, but that's actually too thick for heat transfer application. So I kind of summarized this here by looking at state-of-the-art and looking at where we need to be. And so this first part of my talk is really outlining the understanding of why these blisters form and where we need to get and what we need to handle in order to enhance durability of these surfaces. And so there's actually 2 approaches that we used that I'll discuss. The first one is handling the defects or those pinholes. So we said, if pinholes are the source of the blisters, can we get rid of pinholes and then therefore prevent blisters from going? And so one promising path that we looked at was self-healing materials. These are not new and not developed by us. People have looked at capsule-based materials and vascular materials where essentially once you rupture the material via some defect, it'll release a payload, typically an epoxy or an epoxy resin that will then cure, and then your pinhole will go away. And people have looked at this at Illinois and other places. One thing we liked was the fact that we could use dynamic polymer networks. These materials are quite large, so the minimum size of these capsules is about 1 micron. You can't make them much smaller, it becomes very inefficient. But if you look at dynamic polymer networks or vitrimers, this is molecular length scale. So your ester size is about 1 angstrom. And so these are basically networks where you have dynamic exchange of bonding. And so this is work by Lee, where you could actually take these materials, you could cut them, and then just by pressing them together and applying a bit of heat, they actually fully recover, right? You don't see any more interfaces because of the cut. And so this is the approach we took. We collaborate with a material scientist named Christopher Evans, not the actor, it's an actual material scientist at UIUC. We use PDMS strands with dynamic boronic ester crosslinks. We call this dynPDMS or dynamic PDMS. And so this is kind of the way the cross-linking works and dynamic bond exchange. But really all we did was look at the processing parameters of how we can reduce the thickness and how that varies as a function of annealing temperature. We use things like FTIR or AFM FTIR to actually look at the fact that these BO bonds still remain, even as we go down to very thin formulations. And if you look here, this is AFM scratching. So actually we take a material and we scratch it. And then when we do an AFM scan afterwards, we see that it'll actually self-heal. It'll form a little bump actually. Now, if you look at something like CFX, this is a standard state-of-the-art polymer, your scratch will actually be remaining on the surface and it won't heal. And so this was actually good proof that things are working and working out. And so we then took this, again, nano-indenter, very simple, CFX film results in blisters, well-ordered blisters. dynPDMS film, when we apply the same pattern, we don't see any patterning. It actually fully self-heals. Look at cutting, like glass cutting, CFX film, you actually start forming liquid films inside this cut. Whereas dynPDMS film, you can actually see that it's self-healed and you'll see discrete droplets actually inside the crack itself. And then finally, demonstrating that this works in condensation. Again, we're talking about a 17-day test here, so nothing extraordinary, but we do have results which show that things like CFX will delaminate and our dynPDMS, PDMS will last much longer over time. And so we were excited about this and published this work a few years ago now, but we're continuing it to do larger scale up, which I'll talk about in a few slides. The other approach that I'll tell you about is tailoring the material's intrinsic properties. So you could either get rid of pinholes, which some can argue that you'll never get rid of all pinholes. But given that we know how wet adhesion and Young's modulus affects durability, can we actually make materials that have a high enough Young's modulus and high enough wet adhesion to give us the properties that we want for stable hydrophobicity? And so the one thing we looked at was diamond-like carbon, right? So people have looked at inorganic materials in the past, things like wettability of gold. Gold was actually a large topic of interest for dropwise condensation for 30 or 40 years. But it turns out that most of the non-wetting properties of gold was because of volatile organic compound contaminants that come from the air. And so this is not stable to use in a real condenser. Rare earth oxides were reported maybe 10 years ago now by a lab out of MIT, but it turns out this was also VOC, and this was kind of a scandal. I'll be honest about it. But essentially it's the same effects. What we liked was diamond-like carbon, in particular fluorinated diamond-like carbon. You could co-deposit fluorine or hydrogenated chemistries with diamond-like carbon. DLC is actually used as an anti-wear coating in engine applications, so it's already extremely durable and extremely adherent to substrates, especially metallic substrates. And so we started a project by collaborating with a company called Oerlikon Balzers. They're the biggest manufacturer of DLC chamber deposition chambers in the world. And so what we do is we develop a multi-layer coating, which has different constituents. So you can look at like X-ray intensity as a function of X-ray energy. This is basically an XPS scan. And this FDLC coating, which I'm showing you here, is about 2.5 microns thick, but it's got multiple layers. It's got a titanium layer for adhesion. It's got a nitrogen-rich layer for certain thermal properties, a silicon-rich layer, and then a fluorine layer that's co-deposited with DLC on top, which is about 600 nanometers thick. And so the top layer gives you the function. The bottom layers essentially give you a gradient in mechanical properties just to relieve stress during deposition. And the multi-layer formulation also acts as a prevention or a barrier blocker for nucleation or pinhole formation all the way down to the substrate. If you were to look at an indenter load profile as a function of depth, your DLC material is more metal-like than a polymer, right? 4 GPa versus 78 GPa. So very exciting results, and hopefully it works. Hopefully I show you that it works. If you measure the thermal conductivity of the DLC, it's about 0.3. So you're not gaining much over here. It's still fairly low, but you're mainly going to gain on the mechanical properties. And if you look at contact angle measurements, so this is using goniometry and water for multiple substrates, right? You're getting pretty good hydrophobicity, pretty low contact angle hysteresis. And so what I'm plotting here is advancing and receding contact angle, and these should be dropwise condensing. So, I'm talking about dropwise condensation here. It's important to show you that this will actually work and give you an enhancement. What we do is test in a custom developed chamber that we have in lab. This is basically a pressure vessel where we could actually inject clean steam, get rid of non-condensables, and then mount tube samples to actually measure condensation heat transfer coefficient. And I saw this morning Solomon has a very similar setup in his lab. So I'm glad to see that he's working on good stuff as well. And so you could see that for a DLC coated tube versus a bare copper, you do get a heat transfer coefficient increase as expected, and it's stable over a range of different vapor pressures. The behavior makes sense as well with dropwise condensation. If you look at things like effective exposure time to air and to nitrogen environments, you can see that the DLC, which is basically these solid curves, compared to the self-assembled monolayer, which is the dotted curves, the DLC shows much greater stability. So it's got high temperature stability. And then if you look at the contact angle as a function of abrasion cycle, this is mechanical abrasion in a Tabor tester. You could go up to essentially 5,000 abrasion cycles. You don't necessarily even notice a difference in the top layer. You do have some increase in the contact angle hysteresis, but you still see dropwise condensation even at 5,000 abrasion cycles. So this is a scan, a fib image focused on a beam cross section at 0 cycle and 5,000 cycles, and these are multiple different layers. You can't really differentiate between the two after 5,000 cycles. So good, everything makes sense. Now, how long will it last? And so this is a separate chamber that we developed where we could actually do long-term testing. We could actually mount multiple samples on cold plates and then put it in here. And this work actually started back in 2016. So this is a long time experiment, something which maybe for PhD students, but maybe less so for master's students. And we compare samples to just uncoated HTMS, polymeric, ICVD. And so if we look, this is for copper, aluminum, silicon, day 1 to day 716. So this is actually 2 years. We've gone up to 3 years. And at some point we ended the experiment because it was getting just too hard to maintain. So currently we have the work in review in Nature Communications, in 3 years for us. Sounds very good. Maybe you can go longer. But we're very excited by this work of using DLC. So to summarize this part of my talk, this slide has a lot of words, but essentially we've come up with 2 different alternate coating methodologies to handle this durability problem in 2 different ways. And really got there by really understanding the fundamentals to begin with, and then thinking about how we could tailor the materials and working with the right people to develop systems, material systems to get us there. So you might ask, well, why do I not see this in my nuclear power plant currently? This is where we are now. We're actually collaborating with the Abbott power plant. For those of you who have visited Illinois or who haven't, please come visit. We have a CHP power plant, which is combined heat and power, provides heating for the entire campus, but also power for the campus. The plant itself is very nice in that they're very liberal in collaborating with faculty. And so this is what the inside of the plant looks like. And through my work with Chris Evans and Mike Brewer, who's the head engineer at the plant, we're now working with Kennedy Tank, which is a company in Indianapolis, to actually build a real condenser and test it in the steam line of the plant. So we're talking about sub 1 atmosphere pressure, about 18 PSI, absolute pressure steam. And again, we're now moving away from kind of lab scale experiments with nano indenters to now things that you guys may have learned in like 2nd year undergrad, right? So like CAD, getting extra stainless steel tubing from the manufacturer or coating it. And I really like to flash this because this is now like real applications, right? You start with tubing. One thing I want you guys to notice here is all the grease in these shops. This is not a clean room environment by any means. So you got to coat the tubing. We drop off the tubing. They actually assemble the tube side. They weld it together. How this gentleman handles this is very important in terms of, well, now you can't tell them you can't touch the tube because it's too fragile. It has to be durable enough for somebody with gloves to be handling it, welding it, thermal stresses. On the shell side, that gets manufactured, and then it becomes a shell and tube heat exchanger. And so these are actually coated tubes that we've developed. We've coated for them. You can see some of them are discolored. The darker ones are actually the DLC coating, and we have other formulations as well, like the Vitromer coating as well. And this is pressure testing to make sure that it can actually hold pressure. And so where we are now, this is actually the location in the plant where we want to put it. Again, just to show you, this is not a clean room environment by any means. It's a highly compact, high heat environment. And we're doing things like process flows and sketches on paper to make sure things work. And so ideally, hopefully you see some paper where you have figures like this, where you guys can actually see what the result is in the long run. But we're very excited, and we hope to actually make sure this works in realistic settings over long periods of time. So you might ask yourself, well, Nenad, you talked a lot about steam, but many working fluids are not steam. Many working fluids people use in industry are things like refrigerants or dielectric liquids or mineral oils. And so I like to motivate this next part of my talk by thinking a little bit now about non-aqueous fluids. So if you were to look at the US residential energy consumption by end use, you're talking about a large portion of it going to HVAC and R, heating, ventilation, air conditioning, and refrigeration, about half of your usage. Almost all of these systems don't utilize water. Many of them utilize refrigerant as the working fluid. And so if you could develop coatings to repel things like refrigerants or like refrigerants even more, that's very important. And this is a part of research in our community, which is not typically handled and stayed away from, mainly because refrigerants work at high pressures. It's much easier for a faculty to just work with water because it's safe. Students don't get in trouble. The refrigerants are not refrigerants are flammable. Water is not flammable. You can actually drink your experiment and you'll be fine. Whereas you can't drink refrigerants. So can we actually make surfaces that are repelling to refrigerants? The plot here is actually showing you the CO2 equivalent of emissions of just refrigerant leaks themselves as a function of year. And so most people don't realize that many of the refrigerants that we use have global warming potentials of 1,000 to 10,000. So in terms of CO2 equivalent, even a small emission is actually quite a large impact. And so depending on the use case, we've got a lot of emissions, but this is actually where we want to be. We want to be all the way down here. And what that's driven is actually interest in research and development in what we call low GWP refrigerants. So things like R22, R32 by Daikin mixtures, we're going from GWP of 10,000 to let's say 10. And many of these refrigerants have different properties. The two that we have particular interest in are this R1336 MZZ. This is a refrigerant which is actually used in building chillers. So it's quite large volumes, but when you use them in chillers, you actually have a shell and tube condenser. So it's actually a good, condensation problem to look at. The other one is the 1336 MZZE. Both of these are developed by Honeywell and Chemours. And MZZE is actually used in heat pump cycles, which heat pumps are a very important thing as we electrify society. And so what I'm plotting down here are the working fluids themselves, density. I want you to notice the surface tensions. They're a little bit higher than R134A, and the GWP is quite low. And so one thing we've been developing is a multi-layer, we call it a tri-layer coating formulation to actually be able to repel low surface tension fluids. We first deposit a perylene C layer, which actually smooths out the surface and makes it very flat, atomically flat if you look at an AFM scan. We then have a binding layer, which increases the wet adhesion. And then we have a capping layer, which lowers the surface energy. And it turns out if you look at like ethanol, hexane, pentane, as you go down in surface tension, you could still repel these surfaces with fairly low contact angle hysteresis. And so these are kind of more pictures of advancing and receding contact angles. The 1233 ZDE has a finite contact angle, but it has a very small hysteresis, which I'll show you in a second. And so if we look at things like low surface tension condensation, of course, ethanol works great. This is exciting. Water, we expected this. The interesting part is we could actually get stable dropwise condensation of this ZDE and also this 1366 MZZ, which we were very excited about. This is a very important problem. And when I flash these slides, people don't realize that people have been trying to do this using reentrant features and other kinds of techniques, and it usually fails. But this is actually a smooth coating, which will give you dropwise condensation of a refrigerant. And on top of that, it's an industrial relevant refrigerant for chiller applications, which makes the most sense for this kind of coating. So we're very excited by this. And this is another kind of area which we're pushing over the next few years to really implement it. Okay, so for the last part of my talk, I thought I'd switch gears. The lab I run is quite large and the students are fantastic. And so I thought I'd do them justice by showing you kind of a vignette of the other things we work on that are, again, prevalent towards electrification and translation from very fundamental science to very applied technology, okay? And so one large effort we have is on durable structured surfaces for flow boiling applications. Now, forget about chemistry. This is not, there's no polymer chemistry in this. This is basically taking a metal surface and making it rough. And this has very important implications for things like nucleation and heat transfer physics in two-phase flows. When I say durable, I mean the fact that we tend to stay away from oxides and we tend to stick with etched chemistries where after you etch it, you'll be left with the base metal itself. And so because you don't have the oxide on top, you don't have this interface, which can fail to laminate because of thermal stresses or chemical stresses. And so one piece of work which we've done is looking at refrigerant flow boiling. This is the heat transfer coefficient for these etched surfaces as they compare to a plane or a boehmite surface as a function of heat flux for 3 different mass fluxes. And what you'll see is about a 250 to 300% increase in your heat transfer coefficient just by pre-processing your tube by this etch chemistry, right, which is HCl in this case. Well, we've also worked with Brazeway, that company I mentioned, to look at microfin tubes. These microfins are what they currently use in the manufacturing process to enhance the heat transfer. The nice thing is by using this etch step, you can actually remove these fins and save yourself dye wear and also use materials which you can't use using these microfin tubes because they're too hard. And so this is a technology which we've developed in collaboration with Brazeway. If you look at things like pressure drop, minimal changes, minimal increase, and then durability, this is again 30-day trials. We currently have trials that we want to run for multiple months to make sure this works. And so you might ask, well, where is that used, right? So now if we take that and now we apply it to a macro scale technology, electrification, AI, machine learning is driving power densification of data centers. This is a project where we're actually using those etched surfaces to really enhance the efficiency of heat transfer from CPU, GPU architectures in edge data centers. And so you can look at the metrics, right? We want to do heat capture. You can look at the node density, right, from 96 to 274 kilowatt per meter cubed. The power usage efficiency, we want to go from about 1.4 to less than 1.05. Total design power, 400 to 1,000 watts. So you're moving away from air cooling and going more into two-phase cooling. And so this is where we're actually applying those surfaces and developing those cold plates in these EDM fin surfaces. And what we do is we do flow boiling. This is the inlet, this is the outlet, and then look at cooling of these MCM multi-chip module architectures, which are about 75 by 75 millimeters in size. Okay, so these typically would dissipate about 100 watts. These days with AI architectures, you're talking about 1,000. So air cooling is not going to cut it. And some of these technologies, if you want to keep them power dense, have to be utilized. And so you're seeing here junction temperature as a function of power and how that changes as we vary flow rate. And this is a project with Nokia Bell Labs and Carrier, which is mainly helping on the heat recapture. It's funded by ARPA-E. So hopefully that kind of shows you an example of, you know, fundamental to really apply technological development. Another big effort we have is with icing and scaling up technologies. And I realize there's people here at Michigan too that work on this. Anish Tuteya has a big effort and is a very famous person in icing technologies and coatings. Where we kind of come in is looking at some of these surfaces and now scaling them up, right? Going from small scale to large scale. And so you could see here, this is like a bare heat exchanger. This is a super hydrophobic heat exchanger. And there's a very large delay in the icing time, about 2.5 times. And so what you could do is actually delay your de-icing cycle and save yourself efficiency. So you could see here, if you plot the heat transfer rate as a function of time, your super hydrophobic heat exchanger maintains its performance over a much longer time compared to your super hydrophilic one or your bare one. And so again, kind of more fundamental, but as we go to real, I guess I just put it to play. As we go to real demonstration, this is actually a demo of the heat exchanger, the super hydrophobic heat exchanger on a microchannel Ford supplied heat exchanger that they utilize in an automotive heat pump. And so if you look at the super hydrophobic versus state of the art in this transcritical CO2 heat pump system, you could actually look at your heat transfer curve as a function of time. The red one is the super hydrophobic. You maintain your performance over much longer, whereas the other ones you have to run defrost cycles intermittently to maintain performance. And actually, Mike Meyer, who's here, did his undergrad in my lab, and he was working with the student Kalian, who really developed this technology. And I think Mike is actually in one of the papers as well. So talk to him if you want to know more. So again, if you were looking at heat pump integration, you're talking about a COP of 2.1 compared to 1.5 for a bare heat exchanger. And again, this is very important for heat pumps, because for heat pumps, especially air source heat pumps, you're doing work, mechanical work to extract heat out of cold air. And what happens? Frosting. And so frosting is one of the main limitations for both automotive and residential heat pump systems. And this technology has a very important role to play. Okay. And this is actually my last slide. This is another de-icing technology to show you kind of more fundamental coating level studies to now looking at applying it to real aircraft. This is an electric aircraft de-icing technology, which we call electrothermal pulse de-icing. Essentially, if you have like an ice block, beneath the ice block is a coating, parylene, to actually isolate electrically from the aluminum substrate. And then we have an ITO or an FTO coating on top, which is acting as our heater material. And by applying in a pulse, a high current pulse, instead of a steady heat pulse, you could actually confine the heat right at the interface. And by doing that, you actually just locally melt the ice, and you could actually not have to melt the entire ice layer, and everything will fall off. And so this actually shows you that it works on frost as well. Frost tends to be a challenge because it'll wet the surface, and you'll see here, it falls right off. And so it's a highly efficient way to de-ice surfaces. Most people ask, well, like, why electric aircraft? Don't you have like pneumatic boots? Electric aircraft suffer because they don't have an engine, they don't have bleed air to actually do vacuum or inflate those boots. And so now you have to actually put on compressor technologies, which are heavy and bulky and not reliable. Okay, they're not designed to last the entire life of the aircraft. So because you have access to batteries, you could actually do something like electrothermal pulsing. This requires development of highly compact power electronics. It requires application to real wing surfaces, icing wind tunnel tests, and ideally a technology which will be used in the next few decades on real aircraft. So that brings me to the end of my talk. I want to thank the main postdocs, the students who did the work, my collaborators, funding sources. You might see, you're like, what is the ship doing up here? We have a lot of money actually from the nuclear naval lab, as well as Huntington Ingalls Industries. These actually make the naval platforms, the nuclear naval platforms, like the next generation destroyer, carrier platforms, as well as submarines, nuclear submarines. You could imagine many of these have nuclear systems which produce steam. Steam then has to condense. If you can make that condenser much more compact, especially like on a nuclear sub, you could power densify it and actually have more space to do more important things. Air conditioning and refrigeration center, and then my students who do all the work. I just come and I blab about it, and then I take all the credit. So with that, I'll open it up to questions. I think we have a few minutes. I'd be happy to chat with you.
Questions?
Sure, there's questions.
Yes.
Yes.
So you showed the cool video of the droplets feeding each other water through a pinhole. Is it ever advantageous to have that pinhole so that you get a big droplet quickly that then falls off, or is that always going to cause problems to your interface?
Yeah, so people have looked at that actually. There's a study out of Georgia Tech, I want to say like 2011, when I was a grad student. They used a similar kind of surface where when they deposited the polymer, I think it was by accident because I doubt they thought of this, but the polymer didn't get all the way to the bottom. And so you had a rough surface where it was top polymer coated. So when water condensed, it would condense at the bottom layer, and then it would move up to the top. And then at the top, because you have a non-wetting interface, you need a Laplace pressure to actually break through. So what they saw was exactly what you said. They had a droplet, then another droplet. And what they would notice is this one would go into the liquid and feed into this other droplet. And it's actually an ACS nano paper. If you email me, I could share it with you. People have looked at that and it's interesting. But again, durability becomes the questions. Yeah. Good question. Yes.
With the power plant heat exchanger,
Yeah.
were you able to measure its performance in operation?
Yeah, that's a good question. Maybe I'll go back to the sketch. To the sketchy sketch. So right now we do have, this is the schematic you want to look at. We do have temperature, we have a pressure gauge, and we have temperature readings at the inlet and on the outlet of the cooling water. So from that, we could actually get the overall performance, but the tube bundle itself has, I want to say 13 tubes. So the way it's arranged is we can't actually get performance of each tube itself, but each tube is promoted to have a dropwise condensing performance. Now, we do have a tube, which is a self-assembled monolayer as like a control, and we have an uncoated tube. So we can't decouple like how much performance is getting out of each one. We mainly just wanted to do this to like run it for, right now we're set to run for 6 months and then open it up and then see what, which tubes survived and which ones didn't. Right, so that's kind of the main goal here, less so on heat transfer measurements, more on demonstrating it for companies. Yeah.
Actually, I have a follow-up question on that.
Yeah,
You talked a little bit about the handling of the coated tubes.
Yes, yeah.
Did you see kind of very much impacts of it, or like were you able to quantify that?
Yeah, so it depends on the coating. The DLC is actually like you could handle it. Even at the ARPA Summit, we bought some samples where people could just touch it and kind of feel it and scratch it. It's very adherent, and we're not worried about that one. Like if you do like a silane coating, depending on how you handle it, you could affect it. So there are coatings where you have to be very careful about how they're handled. But that's also why we're very kind of bullish on the DLC, because once you coat it, it's pretty ready to go.
And also compared DLC compared to the silane and the other state of the art, like what's the cost difference?
Yeah, that's a good question. I mean, silane itself, it is used as like silane chemistries are used in microfabrication. DLC is used as well. I mentioned the engine applications. I'd say much less so than silane. But again, even when we work with Oerlikon Balzers, like they're looking for a business case. So they work with us because they're like, look, if you could unlock this for us, we could make the chamber infrastructure to do large coatings, and with any economy of scale, right?
It should,
The cost should come down. So yeah. Yes.
You showed like the criteria you're looking for. Then how predictive is it whether it adheres to the substrate or like trial and error? How do you factor that aspect? Whether the buildings can actually work with the substrate?
That's a good question. That's a very Andre question. I don't have a good theory. I mean, we use like the titanium adhesion layer, and we use materials which we know work. I don't have a good understanding of how you could predict. You could probably do it, but I don't know how you would predict whether a certain material, what its adhesion will be with a certain other material itself. And this isn't like a diffusion process where you can think about like diffusion of one material into the other. It's not a bonding process, but you're doing things like PVD. And so the adhesion typically, when we do it by, if it flakes off or not, it's not a good chemistry. There are certain materials that DLC does not like. I think materials that have like lead inside of it, they tell us we can't do this. So it's not like it works for absolutely everything. But that's important. It's an important question. Yeah.
Just a follow up on that. This DLC coating, like, is there a broader class of materials that this is an example of that you want to explore further?
You're saying DLC?
Well, no, like DLC might be an example of a broader type of material that you would want to investigate further.
Yeah, I mean, of course, any other material which is inorganic. So typically, like things like ceramics, if we could do a metal, like basically materials that have high Young's modulus and high adhesion. And so we do have some work with a person who does density functional theory to be able to then predict like what is the surface energy of certain alloys, because we can't test every alloy, but you could use things like DFT to actually do predictions on overall surface energy. And there the focus is moving away from polymers and moving more towards inorganic materials. And that's kind of the way we'd like to go. DLC was the easy one because it's still carbon based, but it's between carbon and graphene. And so you kind of have that play with it, and you can co-deposit fluorine. Yes.
Yes, building on that question, in the DLC coating, you mentioned you had a titanium
Yeah.
layer for adhesion purposes.
Yeah.
How did you go about choosing that as your adhesion interlayer?
So that one we didn't, that one the company just uses as, there are other materials they can use as well for adhesion layers. Titanium just works very well, and it's known to be a good adhesion layer. And so there's ways we could replace it and we could try other materials. But so far we just kind of stuck with a good base adhesion layer material that they typically use.
Okay.
Yeah. If you have suggestions, feel free to let me know. Yeah. Yeah. I'll go by order. Solomon.
Slide 36, are the tubes ripped from inside as well? Down.
Here.
Yeah.
Yeah, so here, this is actually plain smooth tube, unribbed. And this is just smooth tube etched.
Yeah.
So all of this is just smooth. Did you see this one here?
Yes.
This is just a demo of the fact that it's conformal. So we can now take rib tubes that are what we call microfin. And we don't have to worry about, some effects of, it'll actually etch the tops, but not the bottoms. So it actually works quite well, even on very rough geometries. This is all smooth data. We have measured data for this as well. And so I added this yesterday. Thank God I did it. This is a paper that came out like a month ago in IJHMT. And this paper actually has this same data, but now looking at microfin tubes that are unetched and microfin tubes that are etched.
And the microfins are from inside the tube, not outside.
It's inside. Yeah, the refrigerant side is on the inside, typically, and the outside is air.
And how is the manufacturing process on tubes making those regions inside?
These ones, this is extrusion. So what they do is they literally like jam the aluminum through a die, and it gets extruded with these microfin features. Part of the reason why Brazeway really likes this work is the fact that because of extrusion, and whenever you have small features in extrusion, the stresses are very high on the die. So the materials you have to use are very soft aluminum materials. They would like to go towards harder aluminum alloys that have better corrosion resistance, but they can't because they need to include these microfins. So the reason they like this is because they could actually then extrude a smooth tube with better mechanical properties, and they could then do a post-etch to add the nucleation features and avoid these completely, like get rid of them at all, right? Yeah, yeah. Yes, yes.
You mentioned, I think one of the requirements for the DLC was like a higher thermal conductivity, but
Yeah.
the current coatings are maybe a bit below that.
Yeah, yeah.
So I guess, has there been any progress on ways to be able to improve that conductivity, or are you kind of just limited with, like, are there any additives you can add?
Yeah, it's a good question. There is like a whole vein of research on looking at hybrid coatings. So you could think of like, you could grow like copper microwires or nanowires, and then you could actually infiltrate them with a low surface energy polymer. And then those are kind of like backbones for heat conduction. But again, same thing with all of this, like we've tended to kind of stay away from roughness for any hybrid technology and try to do a slim coating itself. But yeah, there is progress. There's a group out of Carnegie Mellon, a gentleman by the name of Cheng Shen, who does exactly that for like thermal interface materials. He'll grow nanowires on foils and then infiltrate with them with glue, and they're compliant. And he gets effective thermal conductivities, which are much higher than a polymer. And so you can actually use that same approach for Dropwise condensation as well. Yeah, good question.
I actually have one on the follow on the refrigerants.
Yeah.
So what about the chemistry dictates the global warming? That's like an important point to think about. And you said that you have these two new refrigerants which you're looking at, which has a much lower. What?
Yes. I think a lot of it is the radiative properties of the molecule.
Okay.
So basically the molecular structure, if you were to look like the chemistries here, you can actually see the molecular structure. Like R134A is this chemistry, and the MZZE is this chemistry here. And the surprising part is like, they look similar, but even a small bonding site location, even location change itself of that bonding site changes the properties of the refrigerant. And so that would be more radiative properties of the molecules themselves.
And is it less likely? Like I know that all these refrigerants are likely to leak out, and that's why we worry about emissions associated with them. Like, are these newer ones also less likely to leak out potentially? compared to the existing?
The nice thing about the MZZE and Z is these are actually known as low pressure refrigerants. So what they mean by low pressure is typically they'll operate them from 1 to 2 bar. R134A will operate between 5 to 7 bar. So if you use that as a leak proxy, you could say, well, the leak rate would be smaller. But I haven't heard an argument for that, like, oh, we'll use this because the leak rate is lower. I think just assume the leak rate will still be high. And so it's more even than just leaks. It's also reclamation. When the system goes down, the technicians will not like come in with a tank to recover it. They'll just leak it out. Just like let it out, vent it to the atmosphere. It's much faster than them setting it up and reclaiming it. And then what do you do when you reclaim it? There's oil in there. How do you separate it? And so, yeah.
Very interesting. Other questions? Let's thank our speaker again.